This question is about 3 compounds that all have the molecular formula C3H6O2. We've got our first one here, so we'll start with our first one. I'm going to start with this 9.20 peak because 9.20 is sort of a bit unique. So I'm going to use my information. I'm going to start with the delta 9.20. I'm going to say, well, what has it told me about that? It's told me it's a singlet, and it's told me its integration is 1. So what can I say about that? Well, 9.20 tells me it's RC double bond OH. Singlet tells me that there are no adjacent protons. Okay. And my integration 1H of this type. So it's pretty much the little picture I've just drawn. I've got a H with a C with a double bond O and a line, and then the C here cannot have any hydrogens on it. Okay, then my next peak, let's go for a different colour. Let's go for something like red. Let's do that there. I'll say delta 4.10, so we could go to our data sheet. And we know that our structure has got 2 oxygens in it and no chlorines and bromines, so we're going to go for this one because 4.10 falls into both these 2 peaks, but we don't have a chlorine or a bromine. So we're going to say it's of the type RC double bond OCH. It says that it's a quartet. So using the n+1 rule, 3 adjacent H's. So on the next door carbon, there's 3. And the integration is 2. So 2 H's of this type. So let's put all that together. So we draw our little jigsaw piece. It was this type. This was what the data sheet told us. The fact that the integration was 2 said put 2 H's here. And the fact that it was a quartet said put 3 H's next door. Okay, and then our final peak, we've got 1.24, which is probably putting us in the sort of one of these ones. Remember I said group all those together. So delta 1.24, it's just like CH3R type. It's a triplet. So 2 adjacent. And its area is 3, its integration value, so the area under the curve equals 3. So 3 H's of this type. What does that tell me? Well, that tells me it's a CH3 because there's 3 H's of this type and that it's adjacent to next to a CH2. It is actually the same bit of the structure as this. It's just that we're looking at the CH3 bit of it next to the CH2, and here we were looking at the CH2 bit next to the CH3. So we put all of our pieces together now. We've got a H next to a C double bond O, and then we know that the C double bond O is next to an O because our other fragment has that in. So the R group, the H next to a C double bond O, that was from our first bit, that was our blue bit. Let me get my colour pen right. That was our blue bit next to a C double bond O, and we know that the C double bond O is next to an O, which is next to a CH2, that's what this peak was about, which is next to a CH3, which is what the green was about. And if we just double check, we go back up to the top, we've got 3 C's, 6 H's and 2 O's, 3 C's, 6 H's and 2 O's, so this is perfect. This is our first structure, and this is called ethyl methanoate, because the ethyl bit here and the methanoate bit over here, it's an ester, ethyl methanoate. Then says compounds B and C are isomers, structural isomers of compound A. When sodium hydrogen carbonate is added to B, fizzing is seen. So that tells me that B is a carboxylic acid. So B is a functional group isomer of the ester. It's a carboxylic acid with 3 hydrogens. 3 carbons and 6 hydrogens. So that must be B, which means C must be another ester. And we know that our first ester that we drew for A was ethyl methanoate. So what if we swap it round and have methyl ethanoate instead of ethyl methanoate? We had propanoic acid here. We're being asked to predict the spectrum for compound B, the carboxylic acid. So let's take each peak one at a time. We've got the carboxylic acid H. So if we look on our data sheet, we've got a nice carboxylic acid H. We've got the H's next door to the carboxylic acid, so we need to be careful, 2.1 to 2.6. And then we've got end of chains, which would be like the base type, 0.7 to 1.2. So we've got these 3 types. What would our spectrum look like? So we would expect to see 3 peaks, because there's 3 proton environments, and we'll go through each peak and we'll write down, let's have the chemical shift. We'll make it like a little table to save repeating writing. Chemical shift of each of these peaks, integration of each of these peaks, so what would be the relative area, and the splitting pattern of each of these peaks. And we know we've got 3. Extend that down a bit. So our first one, let's look at this carboxylic acid one to start off with. We think that we're going to see that between 10 to 12. There's only one of the green ones, and because it's on an oxygen, the next atom along is this C. It's got no H's. It would be a singlet. There are no adjacent protons. Then if we look at these 2 that we've coloured in orange on our structure, we're thinking that they're going to come out between 2.1 and 2.6. There's 2 of them, 2 orange hydrogens, and they live next door to a CH3. So they live next door to 3. 3 plus 1 is 4, so we call that a quartet. And then our final type, we've got in the 0.7 to 1.2 region, we've got 3 of those, and those 3 are adjacent to 2. 2 add 1 is 3, so 2 becomes a triplet. And that is what we would expect our spectrum to look like.